All right, so for doing this one, you notice we got a right triangle. We're trying to find the unknown side length, which I'm going to go ahead and call x here. It's all side lengths. Therefore, we're going to use Pythagorean Theorem. Remember, a squared plus b squared equals c squared. So in this case, that's going to be 8/3 squared plus 15/4 squared equals x squared. Now, would it have been okay if you had this order switched? Is it okay if I did 15/4 squared plus 8/3 squared? Yes, that's perfectly fine. So there's nothing magical about that order on this side because we're adding them. And of course, when you add, the order of addition doesn't change the answer. Now remember yesterday we saw how to do these sorts where in order to square the fractions, we just square the top and square the bottom individually. So 8 squared is 64. 3 squared is 9. Plus, now we got to do 15 squared, which is 225, over 4 squared, which is 16, and that's going to equal x squared. Now we're into something that's a little bit newer, though. Because yesterday, we dealt with ones that just already had a nice, pretty common denominator. In this case, though, we don't. So we're going to have to do a little bit more work here. I need to get a common denominator. In order to do so, the easiest way to get a common denominator between 9 and 16 is to multiply them by each other. So I'm going to multiply everything in the first fraction, top and bottom, by 16. And I'm going to multiply everything in the second fraction, both top and bottom, by 9. Because by doing that, I make the bottoms the same. And remember, that's the whole goal there, is to make the bottom the same denominator. And so both of these end up being 144. And then go ahead and multiply the tops. I always like to do the bottoms first just because it helps us to remember that the bottom must be the same, that I'm really having to change the top in order to make that the same. So 64 times 16 is 1024. Then we do 225 times 9, which gives us 2025. That's probably the hardest part of that problem right there, is getting the common denominator. Now that we have that, I can go ahead and add my fractions. Remember, we need a common denominator because the denominator part is going to stay the same. So it's going to be over 144, and it's 3049 that equals x squared. All right, so we're in our last step now, which is taking the square root of both sides. All right, and so when we go take the square root of both sides here, the square root of 3049, the top number, it's not pretty, is it? When that happens, we don't want to end up with like some decimal within the fraction. So we're going to go ahead and just do the work and get a decimal value. So I'm going to do 3049 divided by 144. I'm then going to take the square root of that number. And when you do that, we should get an answer of about 4.60 as being x. Now I just chose to round it to 2 decimal places. That's fine. You'll notice the original here, it said give it as a mixed number. We cannot go into a fraction. We can't leave it as a fraction if we get a decimal. I meant for this one to give a nice pretty whole number. Must have been something wrong in the setup. Go fix it for future. But if we get some ugly square root, it gives us one of those decimals that goes on forever, then we go ahead and we have to resort to decimal at that point. Now then, shifting gears. This is where we're going to be headed today. We're going to be doing some graphing practice today. Do you remember seeing the wave x function earlier this week?
Yeah.
This came up on one of our earlier wall map assignments. You're going to be doing some more with it. So I just want to remind you about how we can approach dealing with this function. So each of the problems that you see, it starts you off with wave of x, and it gives you what this graph looks like. It then asks you a problem like this. It says, on the graph, make this graph. Now you'll notice what this graph has in it. It's the same wave x, but it has a +2 in it. So the very first thing you do is you go back and you look to see what wave x looks like. Okay, it's this big wave, and I copy that graph into wall map. You'll notice where the red dots are here. I plotted my first point at the top and the second point there at the bottom at 180. All this is doing is just copying the original graph into our answer. Now, the reason why I start that way is because I can now apply the plus 2. What does a plus 2 added on the end of an equation do to my graph? It moves it up 2. And so what I'm going to do is I'm then going to take the graph that I made and I'm going to drag the points that I plotted each up 2. And if you do, you then end up with a graph that looks like this, and that would be your final answer for doing that problem. Some of you might be wondering, what about these two graphs? What's the difference between them? The only difference between these two, they'll both give you the exact same graph. You can use either one. But yeah, the first one puts your points at the top and bottom. Notice the little red dots in the picture there show it at top and bottom. If you wanted to use the second button, you can. But the second button puts your first point in the middle of the wave, and then the second point at either the top or the bottom. Most of these are constructed in such a way that you'll probably find it easiest to just stick with using the first one, but feel free to play with them if you want to. All right, another example, and this is one that tends to be a little bit trickier to think about when we first see these. Notice this is wave of x minus 270. Well, of course, we are still going to start with the same wave function. So I look up above it and I see what wave looks like. Notice I'm going to put a point at the top here and a point at the bottom here in order to recreate it. And so I draw that graph. Now I look to see, what does the minus 120 do to that graph? What does that do physically to my graph? Yeah, that moves it to the right 270. It's a big number. But you'll notice as we move left and right, they are big numbers. And so minus goes to the right. Now 270, notice, is right here. Well, for the first one, that's pretty easy. It just means that point's going to go over to 270. But the second one, sometimes people end up having trouble with this one because we know we're moving it to the right, but how do I know where 270 is? There's a couple ways you can know it. One way is you literally can do 180 plus 270 and see what that gives you. If you did that, it'd give you 450, and that would tell us where to put it. The other way you can know, though, is notice 0 to 270 is 3 hash marks on our particular graphing grid right now. And so that could also tell me then from here to go over 3 hash marks on it. And so I drag that point over to there. Basically, I'm just dragging each of those points right to 270, and then I have my graph. By plotting the points of the original first and then just dragging them to the right spot, it makes these so much easier to do. I like this graph because it really forces you to process through what is the actual transformation being applied to the graph. All right, and then this is the last one. Now, this is one that you haven't seen yet on WAMAP, but it's one that I think you're probably going to know how to handle. So notice it's again starting with the wave function. But the difference is that we have a 4 out front of it. Well, we're still going to start the same way. We still need to multiply, or I still need to start by taking the wave function. So I look up here and I see where the points are. Notice the first point's there, the second point's there. I copy those into WAMAP, and now that is wave. I now need to apply the 4. What does multiplying by 4 do to my graph? If we think back to where we've seen this before, we saw graphs like 4x squared before. Remember, that took our normal x squared and it made it taller. And so that was what the 4x squared did. With our absolute value graphs, we did like 4 absolute value of x before. That took our normal V-shaped graph that I had, and it made it look tall. As you may recall, what we ended up actually calling that formally was a vertical stretch by a factor of 4. And so in this case, it is also going to be a vertical stretch by a factor of 4. And so what we're going to do then is we're going to take this distance right here, and we're going to multiply that by 4. So right now it's up 1, right? So it's now going to be moved up, and it's going to be instead up at 4. Notice I'm not adding 4 to the 1. I'm multiplying it by 4. Then, this point here, notice, that one's going down 1. Negative 1 times 4 is negative 4, right? So that one's now going to be down at negative 4. And so this one stretches it vertically. It makes it 4 times as tall. Notice that affects both the up and the down, which is something that we have done before, but we haven't necessarily seen how it applies to both the up and the down, because all of our graphs before have existed like entirely above the axis and things like that.